the last section in Chapter 10, and the last section in BC Calculus is another section about representing functions as power series. This is kind of a continuation of what we did yesterday. It's actually saying, you know what, we've done all this calculus, and so basically we're allowed to take different derivatives and integrals of a power series, and when we do that, we get a new series which has the same interval of convergence as the original. So we're going to have, given the Maclaurin series for f of x equals 1 over 1 plus x, which you, I hope, recognize as geometric, find the Maclaurin series for natural log of 1 plus x. So I wrote this one out, but you could figure that Maclaurin series out because it is geometric. And then if we go, what I notice about the relationship between these two functions is that f is the derivative of g. So I need to go backwards from the derivative to get the antiderivative. So what I'm going to do is I'm going to integrate this function from 0 to x so that I can get the antiderivative of 1 over 1 plus, and now I'm going to use a t so it doesn't get confusing about what my independent variable is. The antiderivative of this would be natural log of t. If I plug in x, I get natural log of 1 plus x. Sorry. The antiderivative of this would be natural log of 1 plus t. If I plug in x, I get natural log of 1 plus x minus natural log of 1, which is 0. So I'm going to do the same thing because I did it to one side of the equation. I'm going to do the same thing to the other side of the equation, changing these to t's just to avoid confusion as we do, as we integrate. And I missed one. This should be a t, not an x. So now I'm going to take the antiderivative of this side, and I get natural log of 1 plus t. And I take the antiderivative of this side, and I get, go backwards from 1, and you get t minus t squared over 2 plus t to the third over 3 minus t to the fourth over 4. And so the negative 1 to the n isn't going to change, but when I do an antiderivative of t to the n, it'd be t to the n plus 1 over n plus 1. And I'm going to evaluate that from 0 to x. So this side of the equation becomes natural log of 1 plus x minus natural log of 1. And this side of the equation becomes x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4, etc. And then when I plug in 0, I just get 0. So these guys are both 0, and here is my power series for natural log of 1 plus x. I now have a Maclaurin series for g of x, and I got it by doing an antiderivative of my Maclaurin series for f. I want to point out that we know the interval of convergence for f is going to be from -1 to 1 because it's a geometric series. So now we also know that the interval of convergence for a natural log of 1 plus x is the same. Here's a picture of it. The red is the Taylor series, the blue is natural log of 1 plus x, so it's the natural log function shifted left. And you can see that they really converge on that interval, but they don't as long as we're outside of -1 and 1. All right. So here's another one that we can derive. 1 over 1 plus x squared is easy to derive because it's geometric. A is 1 and r is -x squared. And so then because I recognize that as the antiderivative of tangent inverse, I can say, okay, I'm going to do the antiderivative of both sides. Oh, it's the derivative of tangent inverse. So I'm going to do the antiderivative of both sides. Um, and so I get x minus, I'm doing the same process, but I'm not being as careful as I was with the other one because I know that plugging in 0 to this would also give me a 0. And, oops. So I'm not doing it with the t's this time. I'm not being as careful, but I'm doing the same process. And when you get to that general term, you're doing the antiderivative, treating n like it's a constant. So we would add 1 to the exponent and divide by that. And so there's our power series for tangent inverse. And that also converges from -1 to 1. All right. We can also find a definite integral for a power series. So the way we would do that is we would do the integral from 0 to 1 of this sum. And this is really just a sum of a whole bunch of terms. Taking the integrals of sum means we could just take the integral of each term and then add the integrals together. I can, if I want to, write out a bunch of terms and do antiderivatives of terms, or I could work on just doing the antiderivative of the general term. So that antiderivative would be, well, this is all a constant. 2n plus 2 over 5 to the n is going to be the coefficient part. And then it would be, the antiderivative would be add 1 to the exponent. And so now we have the infinite sum from 0 to infinity of this guy. And we're going to evaluate that from 0 to 1. I can do a little bit of canceling because 2n plus 2 is the same thing as 2 times n plus 1. If I plug in 1, I get 2 over 5 to the n times 1 to the n plus 1. Well, that's just always going to be 1. If I plug in 0, I get 2 over 5 to the n times 0. And I'm taking the sum of that from n equals 0 to infinity. It's no longer a power series. Now it is just an infinite series. So we have the series from n equals 0 to infinity of 2 over 5 to the n. And luckily, because I was asked to evaluate this integral, luckily this is a geometric series. It's geometric, and the first term is 2, because if I plug in 0, I get 2 over 1. And the the common ratio is going to be 1/5. So I can I can evaluate my integral because it would be 2 over 1 minus 1/5. Or in other words, it'd be 2 times 5 over 4. And so that would be 20 over 4, it'd be 10. No, it'd be 10 over 4 or 5 over 2. All right. The last example is asking to do the derivative of that power series. One thing we could do is we could write out that power series and take the third derivative, knowing that most of the terms aren't going to matter. But the other, so method 1, let's go ahead and do that. I'm going to just write this series out a little bit. So the first term would be, if I plug in 0, it'd be 2 times 0 plus 2 would be 2 over 1. And then the next term would be, if I plug in 1, it'd be um, 4 fifths x. These are all going to go away when I take my third derivative. And so then if n is equal to 2, I'd have 4 plus 2 is 6 over 25 x squared. Then if I take my third term, it would be to the third power. So it'd be, n is equal to 3, which would be x to the third. 368 over 625, etc., right? If I take the first derivative of that, I get 4 fifths plus 6/25 times 2x plus 8 times 620 over 625 times 3x squared, etc. If I take a second derivative, I'm going to be really lazy and not multiply. And now I'm on the third derivative. That goes away. And so I just have 3 times 2 times 8 over 625. And that is going to be my, that'd be 48 over 625. And that would be my third derivative. And the reason I know that's my third derivative at 0 is because this term, by the time I get the third derivative, would have a 0, it would have an x in it. And when I plug in 0, that would go away. Method 2 is because I know how to build a Taylor series, I know that the coefficient in front of x to the third has to be equal to the third derivative at 0 divided by 3 factorial. So if I solve this for the third derivative at 0, I get 8 times 3 factorial over 625, which is 48 over 625. So both of those two methods work to give us the third derivative. I personally think this one is easier. The Taylor series is a nice, easy way to find whatever derivative we want for a function. We just need to be at the right power, and that gives us the correct derivative, as long as it's evaluated at the center. All right, that is the last topic of BC calculus. Thank you. Bye.